Recording. Okay, the recording has started. My name is Harry Ricker. Welcome to the May 4th, 2025 Cosmology Group meeting. And I hope everybody had a good week. Um, Jerry has offered to give us a talk today. I think he's going to talk about relativity, or something related to that. Is that not correct?
Well, sort of. Essentially the first postulate, but also just Galileo's original principle of relativity.
All right. Well, if you'd like to start, you can start.
All right. Can you hear me all right?
Yes, I hear you fine. Is
Okay,
everybody?
good. Okay. Well, this time I didn't create slides because the last time they didn't work, and I thought I could just read the presentation.
Well, go ahead.
So should I click share? Let's see.
Oh, so you have something written. All right.
Yeah. Well, I printed out some actual notes on paper, though I thought I could read it through the computer if that's all right.
So I guess you're going to talk about reference frames, and is there a privileged reference frame, something in that order?
Yeah, yeah, I
So
think so.
this is a topic that's a real hot topic of discussion everybody wants to talk about.
Yeah. Well, I clicked on share. Oh, there we go. Okay, let's see. Ah, hmm. It isn't showing up. Ah, I think I have a solution. I can go to my I can go to my notes and minimize the Zoom screen and then read the paper. Okay?
All right.
Okay, here we go. The relevance of inertial frames and the Earth's stabilizing groundwork.
Okay, you might want to
Oh.
explain to us what you mean by that.
Well, I guess I'll get to it. Uh,
What do you mean by earth groundwork? Do you mean earth frame
well,
or
well, it's you know the way you can conduct experiments on Earth, and they turn out highly consistent. Like you can make predictions and such. You understand that that you have an inertial environment with which to you can estimate predictable results. It's the Earth stabilizing groundwork. I sort of coined the term, which is, just I haven't found anything else that explains it. Well, there are other few terms that sort of point at it, but they don't quite say that the Earth's gravity provides it counteracts the accelerations caused by the Earth's spin and orbit around the sun, to where we have a stabilized environment. That's essentially what it is.
all right? Well, that's okay. Go ahead.
Okay, cool. All right. Okay. There seems much truth to Galileo's principle of relativity, the idea that the laws of physics are the same in all inertial frames. He arrived at the example of the ships, where one of them is stationary while the other travels at a given velocity. He realized that within each ship has the same inertial conditions, where you couldn't distinguish which is stationary and which is in motion. This is almost the same concept as Newton's idea that an object at rest tends to stay at rest, and an object in motion tends to stay in motion and travels in a straight line at a constant velocity unless acted upon by an external force. Galileo's idea involved frames, whereas Newton's idea involved actual objects. However, they work essentially the same way. The stationary object or frame and the one that travels at a constant velocity experience the same inertial state. The main factor is that they don't accelerate. and each inertial frame is just as valid as all the others. There isn't one that is fundamentally preferred or absolute. When it is convenient to perform an experiment, one frame is typically designated as a preferred frame. However, this frame isn't absolute, eh, maybe in a grand sense, since you could always choose another frame for the same experiment. Consider the example of how a ball bounces just the same on the stationary ground as it does when it's in a vehicle such as a bus that travels down the road at a constant velocity. The bus and the ground act as two different inertial frames. When there is a state of equilibrium, okay, I'm sorry. The bus and the ground act as two different inertial frames where there is a state of equilibrium where accelerations don't exist. If the bus were to suddenly accelerate or go slower, the inertial equilibrium is interfered with. The difference is immediately detectable, and the ball would seem to travel diagonally instead of up and down. The ball actually continues to bounce in the same fashion. It's just that it's the vehicle that goes at a different pace. You could also apply the same principle to objects in outer space, such as within two spacecrafts. If they don't accelerate, each of them experiences the same inertial conditions within their different frames, where you can conduct a given experiment and expect the same result. Of course, Einstein borrowed and somewhat adapted Galileo's original principle of relativity. With special relativity, he wanted to understand the relative motions of objects. He focused on stationary objects and those that travel in a straight line at a constant velocity. I'd say that even though I disagree with various relativistic effects, it was a good idea to omit the influence of gravity and accelerations completely. This way, he could more closely examine how objects travel without these interferences in order to gain a clearer understanding. If a frame is perfectly centered upon an inertial object, the frame is also inertial. Of course, an inertial frame may also set the stage for various other objects to travel at different velocities or even accelerate through. It symbolically oversees the scenario. Of course, frames don't physically exist. However, they're a highly useful construct. While idealized inertial frames can't exist in reality, other types of possible inertial frames exist, whether they're inertial, gravitational, accelerating, or even rotational. When any of these is consistent, it creates a certain type of inertial frame. I thought I'd call these stylized inertial frames so as to distinguish them as different than inertial, idealized inertial frames, which can't exist since they couldn't experience gravity. When an object accelerates in a straight line, it experiences quick glimpses of inertial frames. Within the conditions of a spacecraft that accelerates, any experiments the astronauts might conduct in a spacecraft, for instance, will turn out the same within another spacecraft that accelerates to the same degree. A rotating frame is commonly called non-inertial. This is understandable since the object within such conditions that it always accelerates to the side to where it creates either centripetal or centrifugal force. Within this environment, any actions or experiments maintain their predictability. Accelerating frames and rotating frames typically don't occur on their own in the universe, if at all. They're human made effects. However, they can generate an artificial inertial environment. The concept of inertial frames is quite valid to consider, even though it is understood that idealized inertial frames don't exist. I previously thought such an environment was possible in distant outer space or even within a zero gravity plane that free falls to Earth. I found out the only factor which prevents inertial frames is tidal forces, which is the influence of gravitational sources in other places within the universe which create interference, such as various celestial objects which exist quite a distance away. So this influence is only detectable with highly precise instrumentation. I would guess that all physical phenomena, such as smaller objects or even a speck of dust, has a degree of influence on everything else, though, even though this influence is incredibly astronomically minuscule. So it seems that almost completely inertial frames exist, even if they aren't precisely 100%. However, it seems thoroughly sufficient to conduct experiments and expect similar results. Without inertial frames or objects, how could we understand accelerations without having something to compare them to? It might sound quite abstract and imaginary. However, these inertial frames seem to have a high level of usefulness. The absence of truly inertial frames doesn't mean the concept isn't applicable to observing the inertial motions of objects. Of course, this is the Earth stabilizing groundwork. Of course, inertial frames work in a different way on Earth compared to outer space. The Earth isn't a truly inertial frame, even though it's an effective lab frame, which provides the inertial conditions to generate consistent results for a variety of experiments. The Earth's gravity makes this possible. It serves as a stabilizing groundwork which counteracts all the accelerations of the Earth's spin and orbit around the Sun. This provides an inertial environment with the presence of gravity. Objects on Earth tend to exist in a stationary position relative to Earth. Of course, objects may fall, or given impetus may propel them into other motions. However, most objects stay at rest if they aren't affected by various causal or environmental factors. However, as human beings, we often take actions that affect the conditions of our environment. The concept of the stabilizing groundwork would also apply to other celestial objects. Within such a frame, there is a consistent level of gravity and a state of equilibrium where physics operates in the same predictable way. However, the Earth's gravity doesn't provide a 100% perfect inertial frame. Years ago, I asked in a forum whether the accelerations of the Earth's spin and orbit is actually detectable. Someone said that there is a highly technical device, the Foucault's pendulum, that can detect these slight variations. So it seems that inertial frames on Earth provide reasonably stable conditions which stay highly consistent, so much so that it requires precise instrumentation in order to detect the variations. How inertial frames exist and when the degree of gravity is the same. So it seems the idea that all inertial frames are equally valid would seem to apply to more than just idealized inertial frames. If two objects or reference frames travel relative to each other, they don't accelerate, and they have the same degree of gravity, they experience the same and equally valid inertial conditions. Galileo's insight was profound and highly useful. The Earth isn't a precise inertial frame, though he realized that the motions of objects act in the same predictable way when the stationary frame and the one that travels at a constant velocity. Galileo's idea works when gravity is present. I'd say that Galileo's principle of relativity is effectively the truth if truly inertial frames could exist. The presence of gravity is only an interference, which is often possible to effectively account for. The absence of truly inertial frames doesn't discount the value of the concept and the role they play with understanding the relative motions of objects. And I have to say, it isn't that much, but that's all. I had way much more, but I sort of whittled it down because it was I repeated myself a lot, and that's basically it, though.
Okay, well, that wasn't very long. Anybody have any questions or comments? I hope we have some.
Well, all I would say, if I may, Harry, just in introduction, I think I've said this before, is because of this fundamental insight of Galileo's, which Jerry refers to, I take exception to using the word relativity or relativistic when one really means Einsteinian relativity or special relativity. Uh, you know, the general principle of relativity for inertial frames, which you've talked about there, is actually valid, but it's Galileo's principle. It's not Einstein's principle.
Oh,
So you
I would
qualify when
agree.
you're talking about Einsteinian relativity.
Well, as I had mentioned, I disagree with time dilation. I didn't mention specifically, but I disagree with various relativistic effects. So Galileo's principle of relativity, I think, is highly valid, even if idealized inertial frames can't exist. It was a profound insight that the relative motions of objects, whether they're stationary or traveling at whatever velocity relative to each other, that the same inertial conditions uh, are provided. Yeah.
I think you gave some examples of non-inertiality. You talked about gravitation, and you talked about acceleration, and then you talked about rotation. But actually, rotation is a form of acceleration, so it's unnecessary
Yes.
to make that
Well,
special case.
I agree. That's why I called them stylized inertial frames. Inertial has the connotation that it travels in a straight line, which is understandable. I didn't know what else to call them. However, the rotational frames, I mean, like if you conduct experiments like in a spinning cylinder, you're gonna have the same result as another spinning cylinder that spins to the same degree that's of the same size. So that was mainly my point there.
Mm.
Does the Earth rotation or decrease over time?
Oh, you mean the spin, like the orbit or the spin? Or,
Both. The orbit increase amount of time to complete one cycle, or the spin of the Earth. Like if you spin a wheel, eventually it stops spinning.
yeah. Well,
So
the Earth
the
spin
question
seems
I
consistent.
raise is the Earth slowing down in its
Well,
spin?
I, I don't know, but it seems consistently over the past millions of years or documented history, it seems to have presented itself as fairly consistent. So I don't know. Maybe it does slow down. I mean, you
Well,
know,
that would seem to be a rather fundamental physics question to address.
well,
Because
I
if
mean,
it's not slowing down,
there's no
what
test that
is
I
the
could perform
source
that,
of the
that
torque
yeah. Well, I
to
mean,
maintain the spin that it
if
has?
if if the Earth spin did slow down, it would seem catastrophic to cities. Buildings would fall sideways if there was a slowing. I mean,
I mean, it
if it
could
was
be a very
gradual.
small amount of slowing that you wouldn't notice in terms
I
of
mean,
buildings falling
maybe it
down.
does. I mean, I don't have a clue.
Yeah, well, I mean, is there a real significance to the Earth slowing down? I mean, if you look at is the Earth really moving on its own, or is it actually part of what, like Mach principle said, it's just part of the universe. So if the Earth slows down, it's because the system it's in is changing too. And could we even tell it's slowing down if that's the case? The other question I had is that, did Galileo ever discuss the behavior of a Foucault pendulum?
Oh, that was way before Galileo.
Yeah,
I
but
mean,
did he ever
that's relatively recent, the Foucault pendulum.
yeah, but did he ever so that's what I'm saying. Did his Galilean theory discuss or would it work with Foucault's pendulum?
Oh,
I mean, that's kind of an exception to the inertial characteristic of the Earth.
the very slightly detectable the detectable motions of the Earth's spin and orbit by the Foucault pendulum. I mean, those are just very minor differences. I mean, just
Yeah, but in
you,
24
you need
hours, the Foucault.
well, you need precise instrumentation in order to detect them. So it seems that Galileo's idea holds, and even if it doesn't, there's generally it still applies. I mean, you can observe, that when you're in motion and when you're stationary, objects fall and land. You can conduct experiments the same. I mean, like relative frames and relative motion, when there is an acceleration, it's the same inertial conditions.
Yeah, but the Foucault pendulum, nonetheless, it rotates in 24 hours. It totally has gone an entirely circular motion. I mean, so
I
it's
think the
not that
Foucault pendulum
difficult to
was
detect over
invented like
time.
a century ago or something, or it wasn't that much time ago. I can't quite remember.
Correct. But does that adhere to Galileo's theory? Or is
Well, I
that
wouldn't say that it
acceptable?
discredits it at all. I mean, like Galileo was speaking generally. He made the observation of the ships, which was valid. You know,
I understand that,
and
but I'm just saying, as
even
Galileo,
though even if it isn't perfect, it points to something. It shows us, hey, there's something there that of the relative motions of objects that when there is an acceleration, they experience the same inertial conditions.
right? I'm just pointing out that Galileo's principle may or may not hold for something like Foucault's pendulum, and that's strictly mechanical. And where Einstein's theory was took in that principle, but it included electromagnetics. I mean, like his original theory was the electrodynamics of moving bodies, which I think the name should have never been changed, because I think once they changed it, it lost its real true meaning, was the relationship to electromagnetic fields to moving bodies, not just mechanics to mechanics. Like
Well,
Galileo's principle is strictly mechanical.
so you mean like the difference between Galileo's original principle of relativity and Einstein's
Is
postulate?
yeah, it's the
Well,
inclusion of electromagnetics.
the scientific standards weren't as high in Galileo's time. He was speaking sort of offhandedly, even though he had a profound observation. However, though, Einstein sort of refined it, even though I disagree with his various relativistic effects. I mean, I agree with the first postulate. And I mean, like Galileo wasn't considering the presence of electromagnetism. He didn't really have a reason to at that point, it seems.
Right, but we can't throw it out today because it is real.
Oh, well,
So,
I would definitely agree.
if we want to
Well,
stick,
shortly after Galileo, I mean, Foucault's experiments were done in the middle of the 19th century, but very shortly after Galileo, Newton looked at this, and he found actually analytically that the principle of equivalence of frames moving at a constant velocity relative to each other came out of his equations. But when there was acceleration, it didn't. This relativistic principle didn't apply. So he introduced this concept of a thought experiment or whatever, maybe a real experiment of the bucket spinning, the Newton's
right,
bucket
Yeah.
spinning. That was pretty soon after Galileo, and there was an absolutivity there because the fluid actually crept up the sides of the container
right.
when it moved. And of course, the Mach principle, which I think you referred to, Cornelis, was that it's you can use a sort of a relativity even for acceleration, but in that case, it's the mass of the whole universe which is spinning around
Right.
the bucket. A strange concept to me, but that's the Mach principle, the strong Mach principle.
Yeah,
Well, 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 sorry.
Well, I'm not as interested in all this, I have to say. Yeah.
Well, well, I can't speak. With the
He's interested in all this, yes.
with the bucket and water example spinning, that's an example of a centrifugal force, which causes the water to to join up to the sides, to rise up to the sides. However, though, that doesn't, I wouldn't say that doesn't discount absolute space, which I think was what he was going for, if I'm not mistaken. Maybe I'm off though.
No, it actually verifies it, I'd say, because
Okay.
there's an absolutivity to space, which can be obtained by looking at revolution. That's what that is saying.
Yeah.
The centrifugal force really is I mean, it's sometimes called a fictitious force because if you sort of work out the equations and look at the vector products and so on, you get these elements. You get in Newton's laws. You don't get just the simple F equals ma. You get these additional terms. And they're called centrifugal force. And there's a Coriolis force as well. And there's an Euler force where if the rotation is varying in time. So, but they're fictitious forces. You have to add them to get the Newtonian force instead of just saying, well, it's mass times acceleration.
Well, I would say they're real forces, though. I mean, you can observe them, and you know, I mean, fictitious in the sense of how, you know.
Well, again, it depends which frame you're looking at it. I mean, from the point of view of, say, a string with a piece of stone which is circling around. Yes, well, from the point of view of the observer, the stone is being attracted to the center because it's not moving off. That's true. There's a centripetal force. But from the point of view of a moving observer or the stone itself, there's a centrifugal force. There's a reaction to that, which is center flying. It's going in the opposite direction. So it depends which frame of reference you're looking at it from.
Yeah, and what you're talking about is like if you were on a merry-go-round that was totally enclosed, so you couldn't see the outside world. It's like being on the ship, except for instead of the ship going straight line, constant speed, it was rotating. You wouldn't be able to explain from the inside of that container, that drum or whatever, why when you threw a ball, it didn't go straight across to the other side or something like that, because you had centripetal force there involved in it, and that would, so that's the kind of like why they call it the fictitious force, because to that observer inside that rotating drum, they wouldn't understand why they couldn't throw the ball straight up. And have it
so in other words, you have to postulate that force, to explain phenomena. Whereas if you're going in a straight line, or you're going on the ship and you're enclosed again and you can't see anything outside, you don't have to postulate that because you don't feel any force. You're in a moving vehicle, and once it's going at constant velocity, you don't feel anything. But if it brakes or if it accelerates, you feel things. So you have to postulate these non-inertial forces.
Right. And that brings it. Yeah, you go back to you were talking, Jerry, earlier about the inertial frame of the Earth being a ground force, where we have to explain. It's more interesting as to why is the Earth apparent the inertial frame, and that's because of like you said, is gravity. It's the way the gravity works, but it's more than that. It's because we can't really see what's pushing us forward, faster at the top to keep us straight. Like a flagpole, why is it standing straight? If there's, if we're rotating, why is it graduated like that? That up higher you can be moving faster, yet you still don't feel any force difference between the bottom of the flagpole and the top of the flagpole. And so it's really, you have to postulate more or less to figure out what gravity was all about to make sense of why it appears to be an inertial frame.
Well, I think gravity on Earth sort of centers things, it stabilizes and creates an inertial equilibrium. If there somehow weren't gravity and Earth would spin, buildings would fall down, like lampposts, it would be chaos. However, the gravity provides that stabilization that provides, that we can act and walk around in a predictable environment.
Yeah. So the question is then, how does it do that? And that's not a question to you. That's just a general question.
Yeah.
And that's the question I think we're all trying to look to answer.
Because it seems quite amazing in many ways. I mean, simplistically, some people, they say, oh, if we're moving at 1,000 miles an hour spinning around, we would feel it, and we don't feel anything. So
Right.
it's amazing how inertial the Earth frame is. And in fact, this leads some of the geocentrists to give very sort of, on the face of it, convincing arguments why the Earth is actually absolutely stationary. Now, of course, when you put to them these small changes like the Foucault 24-hour revolution or something, well, then that's due to the rest of the universe moving around. So they
Yeah.
revert to a sort of a Machian type explanation.
Yep. And that's
So why is that incorrect? So what, I mean, why would you say one view is correct and the opposite view, which is observationally equivalent, incorrect? So you have a geocentric view and a heliocentric view. Why is one correct and the other not if they're experimentally identical?
Well, that's the relativistic view. I mean, Einstein would say, or people who believe in Einstein and relativity would say, well, look, Galileo said the Earth absolutely moves around the sun. But the church at the time said the sun absolutely moves around the Earth. Now, he would say they're both right and both wrong. It doesn't matter. It's irrelevant. There's no such, as you say, Harry, they're observationally they're correct. So which is correct? They're both correct. That's really, I suppose, what follows from believing in special relativity. But I would say, I mean, it's I don't know. It's sort of an ad hoc thing. You could say that. When I apply the brake, I'm moving at a constant speed in a motor car, and then I apply the brakes, and I feel myself moving towards the windshield. Well, you could say that when I apply the brakes, I've made the whole of the universe move in the opposite direction, and that's equivalent. But I mean, it seems to be rather straining what we know. We apply certain forces, and we find that. They do give rise to non-inertial effects, which Jerry has described. So I think it's much more rational to say, well, that they are changing, the speed of the vehicle as against absolute space.
one of the things that
We're coming up on well, let's see, we got 6 minutes.
yeah.
Okay, go ahead. And then I propose that we talk a little bit. Jerry has raised some interesting issues. I see people are interested in talking about it. Okay, go ahead. Just let's be careful not to go over.
I won't be able to join the next session because I will be going to church. But one of the things that I have difficulty with the geocentricist is that I don't quite understand how I can't fathom the stars and the planets and out there in space moving as fast as they are, because they would have to be moving faster than the speed of light. You got not too far from the Earth. The rotational speed, just because of the rotation of the Earth, would have to be so astronomically high. So they don't deny, the geocentricists don't deny that the Earth is rotating.
You're saying that the centrifugal force that applies on the Earth has to apply to the rest of the universe. That's true.
Well, I'm just saying.
I think they might have also thought that the stars weren't that far away from the sun, and that, of course, given we know how far away the stars are, if they were rotating that fast around the Earth, it would be just astronomically fast. I think they thought the stars were small at that point. Just a quick side note.
Yeah, well,
some of these flat Earth people, I think, would talk in that way. But there are some geocentrists, and we've been exposed to some of them, who are very sophisticated. They wouldn't believe that, Jerry. They have the same view, maybe, of the universe as we generally do, the stars being far away. And I don't know how to explain it. I mean, I've heard things. I've heard one, they say, yes, okay, they're going billions of times the speed of light. So what? They don't accept that as a limit. Yeah. I've also heard other explanations. They say, oh, there's a Lorentz contraction, so the thing is actually contracting, and therefore it's not going more than the speed of light. They explain all these things away.
Yeah.
But you'd need to have them in really to get them to explain it, I suppose.
Our accepted modern physics beliefs aren't just explaining things away.
Yeah, but I accept going by the, to intuitively most simplistic method. It seems like usually be the,
Intuitively most simple relative to our small position here on the earth.
yeah, you're right. But that's where the geocentricists are too. They're in the same environment, but they choose to take the less. Anyway, I do have to go, and I think it's about to end. So if anybody else wants to talk, they can.
Good to see you, Cornelius.
Yep. I'm sorry I'll miss the rest of your discussion, but got my priorities. See you guys.
All right, we got 4 minutes.
Okay. See, if you did an experiment on the moon or something like that, I think that would clinch the argument, because the geocentrists are saying, well, the Earth is the preferred frame; it's an absolute frame, and presumably, if they're right, if you did these terrestrial experiments on another planet, you would not find the same as we are saying now, that there was an inertial frame contained by the gravity of that planet. Well, many of us, including myself, would maintain that you would. You'd get a moon centered inertial frame. So that would be an interesting experiment to do to see.
Well, why is it that mainstream says that it's an Earth sun-centered inertial frame?
Your volume has gone a bit low, Harry. Are other people finding that?
Yeah.
Yes, Harry fades.
Yeah, it came back a moment ago, but you've gone back again, Harry.
All right. Well, anyway, my point is essentially that all these arguments relate to picking a particular environment and saying this environment is the environment we prefer to define our physics in. So Galileo said, oh, I prefer to define my physics in terms of the sun. The sun is the center of the universe, not the earth, because the church supposedly said that it was the earth, and Galileo said that it was the sun. And then everybody piled on because they didn't like what the church was doing. And they said, Galileo was right. But was he really right? Why is picking one over the other more correct than the other?
Well, I think Galileo was in an early scientific time. Even though he didn't have things precisely correct, I mean, he might have thought the sun was the center of the universe. I mean, I don't know for sure. I hadn't heard that specific idea.
That's what the whole argument was with the Catholic Church.
Yeah, with
The earth revolves around the sun.
Yeah. Well, I knew
why pick that as the truthful conclusion, which they've done,
why indeed,
as opposed to another conclusion.
Yeah, and perhaps modern science says one thing, but these geocentrists that I've brought up, they actually do say it makes a difference, and they said Galileo was wrong and the church was right. That's what they say.
Well, it's a question of what you want to pick as your frame of reference. That's kind of, so then the question is, what frame of reference do you want to pick?
Well, this discussion, leads to the question of, is there an absolute reference frame? And, perhaps that needs to be examined more carefully in view of these disputes about, is it the sun, the moon, the earth, whatever.
Well, I wouldn't think it's like a celestial object, but I mean, like some might say the ether. However, the objects still travel and exist relative to each other. So I don't think there is a preferred or absolute reference frame, personally.
No.
I prefer to
all right, we're going to get cut off for
reference frame. I prefer to use the speed of light for the reference frame, like Einstein did.
You've come back. I thought you were disappearing.
I just had to. I had to get my tie on and get ready for church.
All right, we're going to get off of here soon.
See you guys later.
Yeah, Cornelius. We'll see you.
For my part, I do work on the basis of a sort of an absolute frame of.
Okay, we're going to continue on with Ian's statement, which he probably got cut short because the warnings didn't.
Yeah, I didn't get the warning, but I work on the basis that there is an absolute space at large. I know these are hard, really, terms to define, but the point I'm making is that that is not to me synonymous with a general ether, because I don't think there is a constant etheric frame. Um, Rather, we seem to have established that celestial objects have their own local ethers, and you've talked about this to a certain extent, Jerry. So there are
I thought
local
that was
ethers.
the point of his talk when he was talking about what is it, the word you used, the groundwork of the
Oh,
earth?
Stabilized.
the stabilizing groundwork.
Yeah.
Yeah, I
So
thought
that
that's
in a
what
way
you.
is a local ether, is it?
Oh, I haven't considered it as such.
Okay, well, it could be considered as such, but I'm just saying that when I say there is an absolutivity of space, I don't mean that is synonymous with a static ether. And I think that was the pitfall of people around the turn of the 19th century, beginning of the 20th century, that they were looking at say, the Michelson-Morley experiment, or they were looking at other experiments, and they were looking at, say, aberration or something like that, and they were getting all these contradictions because, like, if you accept an absolute static ether in the universe at large, well, then the Michelson-Morley experiment seems to contradict that. So
One, I,
hence
I
special
think Michael,
relativity.
I think Michelson and Morley were searching for like a stationary and fixed ether that that like there's other versions where it collects around celestial objects and such, but that they thought it simply propagated light, and like even though they couldn't detect the ether, like the light sources and the sensors were built within the same frame. So, you can expect that the light would travel relative to that frame in that sort of way. And it doesn't at all endorse the idea that the invariance of C, I wouldn't say, which many people have suggested that that's a proof of it, but I would disagree.
Yes. So when the results, either zero or, say, very small results, uh, seemed to contradict the contention that there was a fixed ether. That's right. Um, I maintain, fine, there's no fixed ether then. But that doesn't mean there isn't an absolute frame of reference. They jumped over and they said there's no fixed ether, therefore there's no absolute frame of reference, therefore we'd have to get some extreme view of relativity, such as special relativity, which is congruent with Mach's principle. But it was unnecessary to do that. You can simultaneously reject a fixed ether, which I do, and yet maintain an absolutivity of space. Well, so I maintain.
Well, would you say that there is an absolute frame? I mean that it's space or that it's something else?
Yeah, see, it's a very hard thing to explain. I we're really into philosophy now, and it's very, very hard because I find it very
I
hard
love
to give.
philosophy.
Yeah, sure, physics. So my philosophy, I established some philosophy, which is an axiom, if you like, to work on. And my philosophy is that there is an effective absolute space, which I just call the universe generally. It's not the frame of reference of the sun, or the frame of reference of our galaxy, or the frame of reference of our local. It's not that. It's the universe at large, whatever that means. And that can be taken as an absolute. And certainly, if we do a Newton's bucket type experiment, we can find motion relative to that absolute space. Now, I know Harry has said, well, you could also say that it's the absolute space moving relative to this fixed bucket. You could do that, but I don't do that. I don't accept a total reciprocity with regard to acceleration.
Well, I, I would consider space like more of an open arena where events occur, where objects exist and travel. You know that space is just empty. I mean, like people take issue with me saying empty because, well, it's filled with all these things, and I understand that, but I don't know of another word to explain that space is simply there as a void, though physical phenomena fills fills it to a high degree. I mean, maybe it doesn't completely always, but it seems there's at least the presence of gravity and electromagnetic waves that would occupy that area. So maybe it is completely filled.
See, I think you're right in using gravity and perhaps electromagnetism as well as elements which define, as you call, the stabilized system or this local ether, as I would call it. But the problem is, we really don't know what gravity is. I think we're still in the position that Newton was, that we're just explaining the effects of it. We don't know ultimately what it is.
Oh, I would definitely agree. I mean, even if we don't know what it is, it seems to provide inertial conditions on Earth, though. I mean, that seems a given, at least to me. I mean, that it's observable that you conduct experiments like, just objects that are stationary and traveling at a constant velocity on Earth. They experience the same degree of gravity. They're inertially equal. You can have predictable results of experiments or just ordinary actions, even.
I tend to work along those lines as well, Jerry, but some people use the gravitational field of the object as the determining factor for its local uh, inertial frame, but others use the electromagnetic system. So, in the case of the Earth, you would have, a magnetic field and so on, and therefore you'd have something, electromagnetic generated field. So I'm just saying there are two views. Maybe it's a bit of both, or maybe they're really one and the same thing. Some people say gravitation is really electromagnetic, or maybe electrostatic. In origin.
I have heard that, and Franklin had brought that up as far as, just there being like an electrostatic force that, I mean, because I'd always thought that like with static electricity, that you need ions, where there aren't like atoms that have missing electrons that attract to regular atoms with complete systems in order for the attraction. But he had said that it occurs apart from that. So I haven't looked into that thoroughly though, but that's interesting.
Well, I think Franklin did mention that, but Dennis Allen also has looked into this, and he's written a paper, actually, maybe more than one paper, on the work of Morton Spears, I think is his name, on using a sort of a capacitance type model of gravity, and he's explained uh, things like seismic waves based on this sort of model. So it's an electrostatic model, I suppose, of gravity. Morton Spears, I think it is, Spears. He's deceased now.
Yeah, I haven't heard of that. Hmm.
Yeah.
Well, I'm going to sort of make a comment here. It looks to me, this is how I interpret what you're saying. It looks to me like what you're saying is that the concept of inertial frames would be meaningless if it wasn't for the fact that we were living on the Earth that has a gravity.
Oh no. I'm sorry.
Well,
Well, I mean,
that's my interpretation of what you're saying.
like on Earth, gravity being present is an example. It could occur in outer space. It could occur in any environment where there aren't accelerations with the objects involved. I mean, I would say that inertial environments occur literally everywhere. I mean, if there isn't rotation and there aren't like highly accelerating field, like just if there is an acceleration and they experience the same level of gravity or minimal gravity, because it's impossible to escape gravitational influence altogether, But I would say that, I mean, and to say the term inertial frame, it often brings to mind idealized inertial frames, which I realize those can exist for sure. However, though, the concept still applies and it's highly useful, I would say.
Okay, so what you're trying to do is make a distinction between, so you would say, and I would agree with this, that idealized inertial frames don't exist.
Yes.
Okay, now I could agree with that because I don't think inertial frames exist.
Okay.
I think they're just mathematical idealizations that physicists use to make it so they can solve equations.
Okay, let me give you some comments. I'm so sorry, guys. I
Okay.
heard you. I know you. Everything is okay. But let me tell you, in frames of my model, the cosmic medium is an absolute frame of reference. There is no gravitation, there is nothing, there is cosmic medium. Confirmation of cosmic medium experimental exists, no doubts about it. That's why, what does it mean, empty space, void? I have no idea. But if you have your cosmic medium we live in, you can take it as an absolute frame of reference.
Vladimir,
Yes.
real quick, I'm sorry. Would you say it's possible that within this absolute cosmic medium frame, that there are, sort of local frames of reference that exist and travel relative to each other, where you can deduce what's going on like amongst them? I mean, like even if there is a completely absolute frame, I mean, don't objects exist and travel relative to each other? And,
Relative to each other, move whatever doing. But let me finish my comments, and you will see it's
okay,
simple. First of all, absolute frame. Right now, against this absolute frame, we measured already speed of our Earth, speed of our galaxy, and all the speeds we can calculate right now against this absolute frame of reference. That's why even your questions, one inertial frame, I don't know what does it mean, inertial frame, I don't know. But what is important, one inertial frame against another one, I don't care about it because there is an absolute frame, and please calculate all your movements, all your speeds against this absolute frame. And all the rest is only mathematics and logic and, brains training, and that's it. Nothing special. In physics, there is absolute frame. Measure everything against this absolute frame. That's it. Simple like this. This very important point. Let me continue. The second very important point, the Earth, it's not so inertial as you're supposed to have. I'm sorry, Jerry, where are you? You disappeared.
Oh, his
And I
camera
want to
went
answer
off.
you. I'm sorry. Jerry,
He's back.
you're here. What is important? There is experimental results, and I reported about them, that even spinning of our Mother Earth every day different. Every day they're looking for speed of this rotation. And with variations, about 1, 2 milliseconds, it might be plus, it might be minus. That's why in our time right now, not Galileo time, we know that even our spinning of our Mother Earth, it's not inertial, it's not the same. Every day different, not every year or every orbit position. No, and it's influencing with moon. I put already curved of this variation for 2.5 years, and every week we have a maximum minimum. It's a very stable operation. And what is important, you cannot take Mother Earth as an inertial frame. Forget it. It's changing every day, not every week or century or whatever.
yeah, Vladimir,
And yes.
I have a question. Well, would you say that, okay, if you're in a vehicle on Earth traveling at a constant velocity, and you bounce a ball like in a bus, you bounce a ball and it bounces up and down just as it does on the ground. I mean, what conclusions couldn't you draw from that? I mean, they're two different inertial environments that travel at different velocities.
I tell you, you are on a Mother Earth. You made this experiment today and tomorrow. Today and tomorrow, it's a different spinning of our Mother Earth. It's different inertial reference point, inertial reference system. How to believe it? Which one is correct, today or tomorrow or after tomorrow? Because Mother Earth spinning with a different speed means you cannot rely on these experiments and tell about the inertial system. No, it's not.
Well, the experiments hold true though. I mean, the Earth
You
stabilizing
know, for
forward
3 plus already 4 years, every day, there is atomic clock. You can measure spinning of our Earth with accuracy microseconds.
with highly
We have a
precise
contemporary technique,
experimentation.
to measure it. That's what,
It takes technical instruments in order to detect this. These slight variations don't discount inertial frames. That's at least my opinion.
Well,
we're talking
Jerry,
about
one thing that's
philosophy
not
or we are
clear.
talking about the experiments without philosophy. Because if you're talking about the absolute frame of reference, it's one story. The another story, inertial system in conjunction with Earth, it doesn't work. Even within accuracy 1 millisecond, measured every day different. I can show you this curve and you will be impressed how good it is. I mean, it's not my observations. I gave the explanation of this uneven spinning of our Mother Earth. That's why, man, it's not, you cannot rely on the system that works every day differently. How?
I
I
have a
guess I'm
question for
I
Jerry.
guess I'm not
All
going
right,
to
all
change
right,
your mind, so I won't push it.
all
I
right.
mean,
I have a
you
question
can
for
have your
Jerry.
opinion.
Let's let Jim talk here for a minute.
Okay, I'm sorry.
Yeah, Jerry, you've repeated several times the bouncing of a ball in two inertial frames, on the ground, so to speak, and in a moving vehicle. What is the point of all that?
To show that they're the same inertial environment. When there aren't accelerations within the relative motion of objects,
What
they
does the
experience.
same inertial environment mean? Well, what does
If you
that
don't,
mean?
if you don't understand, I don't know how I can convince you, Jim. I mean, I'm sorry. I mean, to me, it's obvious. I mean, what we all believe isn't obvious to everyone else, so we have to
What
take
is
the
the
time to
it?
explain.
What is the it here?
What is it?
Yeah, what is the it that is obvious? Some proposition that you're making, I guess.
that that all inertial frames are equally valid, that the laws of physics are the same in all inertial frames. It isn't idealized.
That the laws of physics are the same in all inertial frames. Okay.
How
So
aren't they? Could you give me one example of how they aren't, please?
I'm just trying to understand the point that you're making about inertial frames.
Haven't you heard of this idea before?
Well, actually, just about all my life. At any rate, without an absolute frame, and this is a point in support of Vladimir here, without an absolute frame, we have no way to know what the ground state of a particle is, or whether a particle is, so that without an absolute frame, there's a whole lot of things that we just can't know.
What is your absolute frame in your system?
Well, it's the system state, the equations 1 through 6 in binary mechanics. But basically, the point I wanted to make is that I'm in agreement with Vlad in the point that there is such a thing as an absolute frame, and I think we should be seeking the best we can to define that in a way that is satisfactory to a large number of scientists.
How would you satisfactorily define that then? The absolute frame.
How?
Yeah.
Well, one way is that you can determine that the ground state of particles and what they're composed of.
What purpose does it serve to have an absolute frame when there are the relative motions of just ordinary objects all throughout the universe?
Well, without an absolute frame, you
I
have
told
no
already.
idea
No?
of whether an object is in fact moving or not, do you?
We already measured even speed of our Mother Earth against this absolute frame of reference. And you're talking it doesn't exist. Jim, you're absolutely right. I agree with you too. There is an absolute frame of reference. And cosmic medium, this is an absolute frame of reference. We are moving. Imagine you have your liquid and you have your particle, Earth, inside of it, and Earth moving against this medium. Simple like this. What is wrong
Vladimir,
with you? And cosmic
Vladimir,
medium confirmed already with so many experiments, with intergalactic plasma, with infrared background radiation, with microwave background radiation, all of these parts of the cosmic medium. Jerry, what kind of confirmation experiments you mean there is no?
I,
All of them only because of this cosmic medium.
I
The
have a
second very
question.
important point, all the physical laws depends on a cosmic medium only on this absolute frame of reference, only on cosmic medium. You must, in my model, you must only take in and laws the same. You must take into account all the time variation of our so important major gravitational constant, Hubble constant, and all this stuff. That's it.
Okay.
Everything, even
Well,
physical laws, depends on a cosmic medium only,
all right. Well,
not on your
oh,
gravitation, not on a Mother Earth.
okay,
It depends
Vladimir.
on the
I,
cosmic medium.
I have a question. Is your cosmic medium fixed and stationary? How fast does the Earth travel through the cosmic medium, and can that possibly be determined?
It's possibly it's mandatory. It's not possible. Take a look on the Wikipedia, whatever, and you will see
Why
what is the
consider it
speed of
the
the
absolute
Earth,
frame
what
if
is
you
the
don't even know
speed.
where it is?
I don't know what to tell you. First of all, let me finish with cosmic medium. There is cosmic medium. It's proved. That's why it is absolute frame of reference. And how to measure? You can go to the artificial intelligence, to Wikipedia, to whatever. Let me, guys, tell you the last point about Mach principles, because we talked with and Ian talked about Mach principle. It doesn't mean that universe moving against us, all of it. No. In 1938, Dirac he formulated Mach's principle. It's very simple. Local physics depends on some huge parameter in conjunction with the whole universe for him. For me, it's the world. In my model, Dirac large number, it's exactly the parameter we must take into account with all the local physics. You're talking about the gravitation. Please take gravitational constant. It's a parameter, it's not a constant. Depending on this a huge parameter in the 10 to the power 40, about this one. That's why the connection between local physics in uh, all the universe, it's against this Dirac large number. That's it. It's not moving. It's not
Vladimir,
rotating the whole universe. It is
Vladimir.
Let me
stable.
stop you here. Did anybody look at that video that I sent out, or did nobody look at it?
I did. I had a look at it. It was Unsecure, wasn't it? Talking about these.
Yeah, she was talking about Dirac's second large number hypothesis.
Yeah.
You proposed to talk
I'm a bit
today about
skeptical
this
about
Vladimir,
it.
large.
I'm sorry,
Vladimir,
but yeah.
Vladimir.
Yes.
Would you say they have determined the velocity of light on Earth? That they know how fast it goes?
Sorry. Yeah, I misunderstood your question.
Do you know do you know if they've measured the velocity of light on Earth in
And
experiments?
and and what?
I mean, do you believe they have?
They measured not velocity of light on the Earth. Yes, they measured 200 plus years ago.
What for?
And
What? They've done it way more recently. Okay, I'll make it simpler. When you're riding a bicycle down the road at 30 miles an hour, what is that 30 miles an hour relative to? It isn't the absolute frame, the cosmic medium, is it? I'm sorry.
Relative to arbitrary standards of measure.
Well, Jerry seems to be, if we count Ian, Vlad, and myself, as favoring the idea of an absolute frame. I'm not sure about Harry. It looks like Jerry is opposing the idea or usefulness. This is a key term. You're saying that the inertial frames are so useful. Um, uh, okay, I guess they are. You know, like that's why I guess
that's the mainstream position.
So Jerry, are you opposed to the idea of an absolute frame, and if so, why?
Well, it hasn't been really established what an absolute frame is. Okay, is it would you say it's a cosmic medium, Jim?
Well, it's a frame in which you can determine whether an object moves or not, and it's the only frame that you can determine that. And
Couldn't
so
you determine that for many frames, like for many, like as a person, you can look and
because
observe.
that frame could be moving. Any frame could be moving with reference to the absolute reference frame. So the only way to even steady motion, and that's what physics is about to a large extent, and to understand how objects move, is to define an absolute frame, to know whether an object is in fact moving or not.
Jim, if there is an absolute frame, how fast is the Earth traveling through it?
Well, that's a good question. I've commented on that in the past. It's some hundreds of kilometers per second, apparently, according to many observers. There's a wide range of estimates there.
Okay, would you say they have measured the speed of light on Earth in laboratories or countless other experiments where they measure other effects?
Would I say?
Yeah.
What are we back in elementary school here? What is the point that you're driving at? What is the elementary school questions?
He's trying to say basically that if there's an absolute frame, then it ought to be apparent when you try to measure the velocity of light. I think.
Thank you.
So
I would agree with that. That makes sense.
All right.
Well, Jim, when you ride a bicycle on Earth 30 miles an hour, what is that 30 miles an hour relative to?
I guess the ground that the bike is.
Yes, exactly. That is essentially my point.
So, what is your point? That
that the Earth
when you ride your bike, your speedometer gives you some useful information.
Okay. If what you haven't like clearly established what your absolute frame is, but when you look at the bicycle,
yes, I have.
Traveling on
I
Earth,
presented right here in these sessions equations defining the absolute frame.
When you look at the bicycle traveling on Earth, you don't go by the absolute frame that you're mentioning. You go by the Earth, the ground.
Yeah, because we're living on
that's my point.
Practical, yes.
Well, but I don't understand what that point is. In other words, you're more interested in bicycles on Earth than science. Is that what you're saying?
Yes, that's exactly what I'm saying. Thank you for clarifying that point, Jim. I'm sorry. I think you're a cool guy. I just want to relate and discuss ideas. I don't mean to get into arguments, I promise.
See, another definition, and it may be coterminous with some of these definitions, such as the one Jim gave about ground state energy, is a frame relative to which the cosmic microwave background radiation is isotropic. So that's one definition of an absolute spatial frame. And that may be coterminous with Vladimir's ideas as well about the medium. I don't know if he's there.
Yeah, we lost Vladimir. I think that assumes that the cosmic microwave background radiation is not local. Some people claim that it's local, but I think Vladimir argues that.
Okay, that's another point. Yes,
Let me clarify that I think Jerry has a great head and a great mind, and we're producing great discussion here, Jerry. There's nothing personal. I love you as a brother.
Oh, thank
Okay.
you so much.
Okay, I want to interrupt here. Jerry, are you aware of this book? The Leibniz-Clark correspondence. Have you ever heard of this book, Leibniz-Clark
I
correspondence?
haven't read that.
I suggest that you're basically this book kind of documents this whole discussion that we've been having between Leibniz, who was the relativity proponent. He proposed relativity, and Clark, who was essentially promoting the Newtonian absolute viewpoint. And so we're still arguing and talking about this debate. Okay. And this book was published several hundred years ago, 300 years ago now, I think. So this is a debate that's going on for a long time. It's not a new debate.
Good clarification, Harry.
Yes, I would like to point out that Newton was an advocate of an absolute frame. And he had the argument that that was the sensorium of God. The absolute frame of reference is the sensorium of God. Now, he sort of invoked religious ideas in saying that, and I think that might sound a little strange to people today. What he actually meant by that, I can't really explain, but to him, he would be saying, I think, that the universe defines the absolute frame. That's what I would interpret him by meaning when he said that it's the absolute frame is the sensorium of God. He's trying to say that the universe, what God has created, is the absolute.
Well, I would say that even if Newton did believe that maybe there are sort of lower subframes. I mean, with this statement, an object who rests in the state at rest, an object in motion is the same motion, it travels at a constant velocity unless acted upon by an external force. I mean, that idea points to inertial frames, even though he specifically referred to objects. If you put a frame around it, it applies exactly the same. I mean,
but the point is that you don't know if without an absolute frame, you don't know if an object is in fact moving at all.
Why?
Well,
because
why?
Well, I mean,
you're limited by your.
I mean, here we
Because
are
you're
on
saying that in
here we
one
are on
frame the
Earth.
object is motionless, and the other frame is moving.
Well, Jim, here we are on Earth. We don't know what the cosmic medium or absolute frame is. We don't know how fast the Earth's traveling through it, but we can look and we can observe. We can see objects moving by. We can see cars going by. We can realize, well, hey, they're moving fast relative to me. There's a bus going by. You can bounce a ball just the same as I do on the ground. They're valid inertial frames.
Right, but I guess the point that I'm getting at is that for advances in fundamental physics, we need the absolute frame in order to define a number of things. Like, for example, if just to understand motion and how things move, it's the description of motion is just the first step in science. Observation is just the first step. What the goal is how the objects move. And if you can't even determine if an object is in motion or not, you're inhibited from exploring that scientific question. So you need an absolute frame in order to determine if an object is in motion, and then when it is in motion, you can then study how that motion occurs.
Jim, what is your view of what the absolute frame is?
Well, I give the first 6 equations of binary mechanics as my definition.
Is it
I
fixed
presented that
stationary?
here in the sessions some time ago.
Is it fixed and stationary?
As an absolute frame, it is stationary
Yeah.
unto itself. Yes.
I mean, so is anyone fixed with that frame to where they can observe the motions of objects? Is anything in the universe fixed right on that frame?
Well, I don't know.
Well, then, why is it necessary to have that in order to observe the relative motions of objects?
I'm not interested in the relative motion. I'm interested in absolute motion and understanding motion itself. And in other words, I'm interested in science. You're interested in how fast your bicycle is going.
I'm interested in science. I promise. I love bicycles. I haven't ridden one in years.
I'm just picking at you, Jerry. But I'm trying to drive my point home that in order to further the science, we need an absolute frame. I've defined same mathematically and can simulate things with my software and so forth. And so I can determine the composition of elementary particles and whether or not they're in motion, and when they do move, how they move. And I presented all of that here, so I don't want to repeat all of that. But, that's the argument for needing an absolute frame that is required in order to advance physics.
Well,
how does physics advance if you know how fast your bicycle is going?
Well,
I mean, that may be
it applies to
convenient.
way more than bicycles, Jim. I mean, like all of the scientific experiments ever performed on Earth were done within this inertial environment. They didn't go by the absolute frame that you speak of.
But as far as I know, it's not an inertial environment. Isn't the Earth rotating?
Okay, it's an almost inertial environment. There's a presence of gravity, but when the gravity level is the same for all the inertial objects involved, when they don't accelerate,
so you can
they're
define
equally
an
valid.
inertial
Okay, the
environment.
Foucault pendulum can detect slight variations. That doesn't discount the overall meaning of the concept, which is highly valid. Even if idealized frames can't exist, it doesn't discount the concept of inertial frames and how they play the role within the motions of relative objects.
Well, that's fine with me, but like in order to advance science, I think we need an absolute frame.
Science has advanced profoundly through the use of our earthly based inertial frame.
Yeah, that's the low flying, the low hanging fruit has been picked. I agree with you. Now we're getting into the hard stuff.
Okay.
They're the mainstream sort of in this kind of pitfall where they're sort of waffling between Einstein was right and an absolute concept, and they're sort of waffling around, and I think that shows that that there's still this ambiguity there. Now, this book, I suggest you take a look at this book, Jerry, because
I'll look into that.
And it's Leibniz-Clark controversy. Most of the issues that you're talking about are talked about in this book, and most of the arguments that we're talking about here are basically presented back and forth between the Newtonian absolute idea and the Leibnizian relative idea. And they didn't really resolve their argument. Now, Newton had to introduce this other idea about relative. He had a concept of absolute. So the way he defined things was there's this absolute. And then he defined relative concepts. He said, well, there's a relative frame of reference. There's relative time. There's relative space. And that was his attempt to resolve the conundrum, if you will. That prevailed up until the late 19th century when they began. Okay, I started the recording. Okay, I should have been paying attention to the clock, and I let the heat of the moment. Yeah, I got involved in the heat of the moment. Anyway, my point that I was really trying to get at was that in the 19th century, Newtonian ideas did prevail, and then towards the end people became dissatisfied with his absolute idea, and then there was a transition back to the relative viewpoint, which Jerry seems to be advocating. And then Einstein sort of took over physics with his relative point of view. And I think the issue really kind of becomes, was that something that's still satisfactory to us? Are we happy with Einstein's relativistic interpretation of physics and their way they've constructed the models of the universe and cosmology based on that relativistic view of physics? And I think that what Vladimir is saying sort of suggests that there's not a lot of satisfaction with the complete relativistic view of cosmology, and that there's a big tension there. It seems like it doesn't make sense to have a cosmology based on a relativistic physics when everything seems to want to point towards an absolute cosmological view of physics. That's kind of where I think we stand now.
And in addition to that, I might mention that there's popped up recently, and I think Harry actually cited some of these videos on YouTube and elsewhere, I guess, that the Big Bang model is now in a big crisis because of the JW ST results of seeing complete galaxies. That it looks like the headlines are saying that Big Bang Theory now in jeopardy and blah, blah, blah. So there's a lot of uncertainty all the way around here.
Yes, I'm sort of, a couple of things about what Vladimir's ideas are, I think, are attractive. One of them is he has this idea of a cosmic medium, which puts absoluteness back. I can see why people would object to that. I get the impression that Jerry is objecting to it, but let him speak for himself. I think that's attractive, so I guess my point of view here of what I wanted to say about this was, it looks to me like what we've done is we've constructed physics from a very local point of view of the Earth, and we've created all this physics that's basically based on our experience on the Earth and what we know. And that physics is sort of coming apart as we look out further into the universe and we try to figure out what's happening outside of us. And I think that's kind of what the issue is. Our physics that we're based on thinking about cosmology is completely locally created and temporally locally created. So if the fundamental constants are changing, what we're thinking and how we're interpreting the universe as a whole, it could be completely wrong because these constants could be changing. But we're still holding on to the idea of that the constants are fundamental and don't change.
Well, I would say with special relativity that Einstein distinguished the first postulate apart from Galileo with the inclusion of electromagnetism, which is reasonable. However, though, and he wanted to account for the invariance of C, which I think the way he went about it was way off. There isn't time dilation, all these other relativistic effects. But I think I agree with the first postulate, and I think the second postulate, the invariance of C, is possible, even though there's much debate about it. But I have an open mind when I'm looking at the experimental verifications that I see here and there. It's just I'm undecided on the second postulate, but I would say I agree with the first, though I don't agree with the rest of special relativity at all.
To further clarify, my understanding is that Jerry is not necessarily against or opposed to the idea of an absolute frame, but just questioning, is there good evidence that such a thing
Yeah.
exists. Is that a fair statement, Jerry?
Yes, very much so. Thank you.
Okay, thank you. I wanted to clarify that because it could be that we or me, maybe we're portraying Jerry's position erroneously, and I'm glad to clarify that. In other words, he's got an open mind on the subject.
Thank you.
Here's a comment of Harry about the physics of 19th, 20th century and so on and so on. We built our theory based on 2.4% of visible matter in the universe. How good it might be? You're talking about the classical physics built on Earth on 2.4% of overall matter of the universe. How we can rely on these experiments, rely on these ideas and laws based on 2.4% of matter? Let me ask you this question.
Well,
Guys,
Vlad, in the 2.4%, are you talking about in the visible spectrum to the eye or the total electromagnetic spectrum?
no, I mean protons, electrons, neutrinos, and that's it. Photons, electrons, protons, neutrinos. All these particles overall in our universe, it's only 2.4% in macro objects, 4.8% in cosmic medium, and all the rest, let me ask you the question, what it is? That's why, Jerry, it's a very good point that we started from Galileo. He couldn't see anything without eyes, only with eyes. That's it, simple like this. And rely on these results based on eyes in contemporary physics, it's not fair, guys. We live in a totally different physical society right now with different, ideas. And what is important, we can calculate even energy density of this cosmic medium, of everything. And to refer to Galileo, it's good. I like it very much. For Mother Earth, it's very good to measure the bicycle speed against the Earth. That's it, simple like this. But we are in business of cosmology right now, guys. And my interest is, what about moon? What about Earth? What about sun? What about everything around us, around the world? And even taking all of them, galaxies, stars, everything, it's only 2.4% of matter. All the rest, what it is, Jerry, what it is. It's exactly
Everything you mentioned acts according to the same physical laws, of course, and that includes the idea that all inertial frames are equally valid. Even though idealized frames can't exist, it isn't just your eyes that observe that the ball bounces the same in the bus as it does on the ground. It's a
Jerry,
realization.
please define what do you mean inertial? Words, inertia, I don't understand it.
Without
I'm physicist.
without acceleration.
How can you acceleration if you don't have system?
When
Absolute system, reference system.
when an object travels at a constant velocity, or if it's stationary relative to whatever.
Constant velocity. What does it mean? Against what?
Okay,
Guys, you are talking about the notions and there is no definition. Inertial system, what does
There
it
is.
mean?
Okay, Vladimir, if you're sitting in your car and you're stationary, you don't feel any inertial effects. Once you slam on the accelerator and you start to move forward, your head goes back and you feel the force of the acceleration. It disturbs the equilibrium of your inertial environment.
You sit in your car. You cannot tell even you are moving or not because you don't have a reference system. You must measure this year. You
You can
moving,
tell
not
when
moving,
acceleration
against what?
happens, though. You can tell when
Huh?
acceleration happens. It disturbs the equilibrium.
You talking about acceleration. I'm talking about movement. You told me inertial system, movement against inertial system. What does it mean in your view? Acceleration. No,
I
you want to neglect
just
the
explained it.
acceleration.
It's without acceleration. When you're stationary or when you're traveling at a constant velocity, it's identical. It's identical inertial conditions. And when you
Well,
speed
I
up,
think
Einstein was.
when you speed up
Oh
more,
my goodness.
when you speed up more, you feel the acceleration, and then when you slow
Jim,
down and
try
peak
to
off,
explain,
I think
Jim, what
the
I mean, because you're on the right track.
I
Jim,
I think this all this discussion of inertial frames, not necessarily just by Jerry alone, but that we've been having by many people over many years, is a just a clever way to avoid the basic question: is an object in motion or not? And we need to be able to determine that in order to understand the mechanisms of motion. As long as we're talking about this inertial frame or that inertial frame, it seems like we're talking about Newton. That object remains at rest, or if it's not at rest, then it continues to go on infinitely. Without change in its velocity. But of course, we know there's friction and what have you, which will slow an object down.
that friction is an external force which slows down the natural constant velocity, though, that creates the inertial conditions. The friction, gravity, accelerations, anything that disturbs a constant velocity or a position of stationariness.
Well, I'm all
Those
in favor of precise and extensive descriptions of motion, but I think physics as a science needs to advance beyond that to determine the mechanisms of motion. And of course, I've written papers and made presentations right here on that subject. So I don't want to toot my own horn, because what I was saying could be incorrect. But correct or not what I said, I do continue to believe that we need an absolute frame in order to, in the first place, define whether an object is in motion or not. How else could you study mechanisms of motion unless you could do that?
Okay, an object in motion can mean many different things. Well, at least two different things. It's either an acceleration, or it's traveling at a constant velocity relative to a stationary object, or just relative to other objects. If it's
doesn't mean constant
if
velocity.
if it's
One step.
if it's accelerating, it isn't
Jerry,
inertial. Yes.
what does it mean, constant velocity? What do you mean?
It means they are traveling relative to another reference frame or object
To another reference
at a
point.
constant
And which
velocity
one? What do
where
you mean
there aren't
another one?
accelerations.
You see,
Well,
you
it can
cannot
be
go
slightly
without
circular reasoning.
additional reference system,
But
man.
remember that Galileo himself, who developed this
Oh,
basic
man.
fundamental principle of relativity, if you like, at constant velocities, and Newton's work is consistent with that, as you pointed out, the first law. But Galileo and the church, if you like, were in agreement, fundamental agreement on the point that the question at issue was of importance and was of significance. They both agreed on that. Whereas modern physics, relativity, including general relativity, which has extended this principle of reciprocity to acceleration and gravitational effects. Modern ideas, the consensus of modern mainstream ideas, is that the argument that they had was irrelevant. It was superfluous, because it doesn't matter whether the Earth goes around the Sun or the Sun goes around the Earth. It's only a matter of convention. So it seems to me from this discussion that many of us actually would agree that the question at issue in the late 16th century was actually a real question. So that there is some sort of
and it's not only was it a real question, I would maintain it's not resolved. It's not answered. It's a remaining and unanswered question.
What is unanswered?
You think there is an answer to it, but it just that we don't have the answer yet. Is that it, Harry?
Well, yes. Uh, I don't think modern physics really, they don't have an agreement. They're oscillating around. For a long, as I described earlier, there was Newton had this idea. There was an absolute thing, the sensorium of God, that he built his theory on, that there was an absolute, and Leibniz argued with that. Okay, I belabored that point. And then, Newton sort of prevailed through the 19th century. And then towards the end of the 19th century, there was kind of reaction against that. And then Einstein came along, and then things kind of flipped over to the complete relativity viewpoint. And, then they built all their cosmology based on this relativity idea, which kind of, it's hard to really understand what it is and what it means, and what is the universe based on that general relativity idea. It's just an abstract math thing. And now they seem to be sort of questioning that. There's not a whole lot of confidence in that. And that seems to be where we stand. That would be my view of it.
And of course, the Newtonian sensorium, this sort of divine definition of space, is one view. But the modern geocentrists that I referred to earlier, they would say, well, that absolute sensorium is actually the Earth reference frame, because the divine has given us a special position, and we're unique in the whole universe. There's nothing like us, and we are the absolute. So in each case, they're defining an absolute based on some sort of theological concept or whatever.
I think the issue is you need an absolute. And the argument is, what is the absolute that you want to pick? And that's what the disagreement is about. What is the absolute? And Jerry comes along and says, how do you define the absolute? You can't define what is the absolute. So that seems to be the problem. The issue is picking an absolute.
Why is an absolute necessary?
Huh?
Why is an absolute frame necessary, though?
Well, that would be a philosophical question that I'm trying to get you to address. And the answer,
I think it's a scientific question also.
Yes, but they're related, because
I think it's both.
Science is actually a part of philosophy. They're basically the same thing. They're different ways of approaching questions. And I guess my point I'm trying to get at is, I think you need an absolute. Physics is really based on absolutes when you really get right down to it. In order to make a measurement, you have to have an absolute. You have a standard of measure that's an absolute. And what we've done is, and time is a good example of this. The first one was the year. Time is defined by a year, the Earth moving around the sun. Then it became the rotation of the Earth, the sidereal time. And we had the issue in the meeting with Ian, where Franklin said, how did they measure time 300 years ago? Well, they measured the rotation of the Earth. That was their calibration. Okay. And it turns out that's not completely accurate, because, as Vladimir pointed out, the rotation time changes. So they said, well, now we've got these atoms that vibrate, and that's our new absolute standard. So what physics has done is changed absolutes over time, if you will, to something that they think is more absolute than their previous standard.
Well, what is important, guys? Even Newton, he introduced physical ether. Why? He needed this absolute frame of reference, for all his laws. Why he introduced this physical ether? It was his definition. We don't know his opinion about does it mean physical ether, but all his laws he told against physical ether. And why all these 200 years at least, people, they tried to prove that physical ether does exist. Why? Because of Newton. He introduced this luminescence, ether later, and so on, guys. That's why it was not us, him. He introduced this notion.
Well, that was an early time in science. Like, I mean, the standards weren't as, demanding. However, though, I wouldn't say that I'm against preferred frames if it means that it's a frame that you can choose in order to perform an experiment and determine the result, such as with super colliders on Earth. They don't go by the absolute frame of wherever that it is. They go by the Earth. That's the way that they determine their results.
But that's just a matter of convenience. I mean,
I'm sorry.
do
Yes.
you concur, Jerry, with the current view that an absolute frame is meaningless? I mean, you've just said that it can be useful and where it can be used,
I'm
but
just questioning what it is. I don't understand.
One sec. Jerry, let me ask you the question. Do you believe in microwave background radiation? Do we have it?
If it exists and the evidence
I'm
says that
sorry.
it does,
I
the
ask
evidence says
another
that
question.
the
We
evidence says
measure
that it
temperature and
does.
all this
I
stuff
don't I
of this
don't think
microwave
it I
background
don't
radiation.
think it's a frame of reference that everything goes by. I'll say that.
Okay. It means the cosmic medium does exist at least because we have microwave background radiation, correct?
So the cosmic medium exists stationarily relative to the cosmic background radiation. The cosmic medium does. It exists
The part of
stationary.
cosmic medium in my model is microwave background radiation. There
Oh,
is fast.
okay. I thought you
Okay.
were saying that it's composed of protons and electrons and
Yes,
photons.
yes, yes. One sec. The next question. There are so named fast radio bursts. People they measure them at least for 20 years. They calculated concentration of intergalactic plasma 4.9 plus minus 1.3% of overall energy. Do you believe because for, this fast radio burst, it's a pure classical physics, it's a plasma physics, I absolutely agree with all of these laws of plasma on Earth. They calculated and they found 4.9 in my model, 4.8% concentration of proton in the intergalactic plasma. Do you believe in experiments? For fast radio bursts, they're measuring the characteristics of intergalactic plasma.
Okay. I mean, I'm sure that that's definitely true.
Yes,
It,
it's
it,
definitely true.
it,
You
it
see, we
doesn't give
have
any
already
credence to the idea that there's an absolute
two
frame, though.
components of the medium, cosmic medium we live in. We believe that microwave background radiation does exist, not believe. We measured it. We believe in intergalactic plasma. We measured it by fast radio bursts. It's a very good experiment, clear, without any supposition, nothing, only plasma physics. And you see that the delay of one component of radio waves another against another one, and you have this distance between them, and you know the difference in wavelengths or frequency of these wavelengths. That's it. And they are measuring this distance between them on a regular basis. And you can tell me, what does it mean? What kind of plasma these radio waves must go through to have this delay on Mother Earth with two different components of the same burst? Simple
Okay.
like this. And you told me that there is no confirmation of cosmic medium.
That's very interesting. I don't see how that
It's
proves
not
an
interesting. It's
absolute
a
frame.
physics.
I don't see
It's
how that proves. I
experimental.
don't see how that proves an absolute frame, though. If these phenomena occur, fine. That's really cool. I don't see how everything, all the motions of all objects that you refer to this cosmic medium as, well, that's how fast it goes relative to this. I mean, like experiments on Earth in super colliders, they don't go by the cosmic medium. They go by the stationary relative inertial conditions of Earth.
You know what? There is no inertial system Earth. I don't understand even inertial system. You didn't give the right definition, not yet. Many times I
I
ask you this
explained it,
question.
Vladimir. I'm sorry. I'm
Constant
sorry.
velocity against what? You're talking many times. Constant velocity. What does it mean?
It
You
means
must
it
measure
means there
velocity
isn't
against what?
there isn't acceleration. Okay, would you say that objects can move? That objects can travel? Would you grant that objects can travel?
Move, if it moves, means against what? You must
Okay,
have some reference
I
point.
agree with
You
that
move
as well.
against what?
Okay, it may be stationary if something's moving with it. It's stationary relative to that. But if something else, it may be moving stationary. Something may be stationary relative to whatever, and it's moving at a constant velocity. Okay, constant velocity means that it doesn't accelerate. It's as simple as that.
Relative,
Jerry,
you told me
hold on.
relative against what? One more
Okay,
time, you talk
hold
right
on.
now, relative
This is a
to
key
anything.
point. This is a key point. Thank you for bringing this up, Vladimir. So, Jerry, what he's saying is without some absolute, how do you know what constant velocity, moving with constant velocity means? That's, you understand
Simple
that?
like this.
Yes, of course.
Jerry, you're absolutely right.
It means there isn't acceleration. Okay, if an object can
No,
move,
no. That's an inference. You've made an inference about constant acceleration
Harry,
from the definition that you never really established to begin with.
Harry, would you say that to determine how fast anything moves, you have to look at the cosmic reference, the absolute frame. That you can't just use other stationary or relatively moving objects to say, well, according to this, I'm moving this fast. Do you see
Right.
what I'm
Now,
saying?
what Vladimir is saying is that what Newton is saying is Newton is defining acceleration relative to constant velocity. And what Vladimir is saying, how do you define constant velocity? So you're in a circular
I've
thing.
already explained.
Well, you think you did, but the point is
What am I missing? What don't you understand? And I'll try to clarify.
the point is that the definition of inertial frame is not really meaningful in a physical sense. It's an idealization. So
Harry,
you built a hold on, you built a theory of mechanics. Okay, Newton says that it moves at a constant velocity until a force acts on it. That's his definition. But you don't know that it's moving at constant velocity unless you have a way of measuring it. So he's basically introduced what a force is in a circular reasoning way.
yeah.
You understand that? That's what Vladimir's trying to point out.
Yeah, well, that's cool. Well, I mean, as far as any object that travels in the whole universe, if it doesn't experience acceleration,
Yeah,
it's
but it can't.
inertial.
That's the point. We know it can't.
Well, so every object experiences acceleration?
Well, I mean, from Vladimir's point of view, he's talked about this quite a lot. Galaxy clusters are rotating around, galaxies are rotating around other galaxies, galaxies are spinning, stars are rotating around the centers of galaxies, planets are rotating around stars, stars are rotating around each other. So everything's moving around everything else, it seems.
Yeah,
Jerry,
I would agree.
Let me 1 second, Jerry. Let me ask you another question.
Okay.
You're talking about the acceleration. What do you mean? How you measure your acceleration?
It's when the inertial equilibrium is disturbed. I mean, like,
Acceleration is meter per second squared. Let me ask you the question.
Yeah.
What does it mean, acceleration in your system?
you may
What
not
does it
be
mean?
able
How
to
do you
determine
measure
it. Okay, when I get into a car and I accelerate, or even if I'm going at a constant velocity, I slam on. Listen, even if I'm going at a constant velocity, I slam on the brakes. That's acceleration in the opposite direction, which they call deceleration. It's a disturbance of the equilibrium. My body either jolts forwards or moves back in response to the impetus of acceleration when there was constant velocity before.
So I don't understand constant velocity, and I don't understand what do you mean acceleration. No. Don't smile. It's definitions, notions. Smiling
I
is
don't know
good
how else
answer.
to
I
explain this
understand
to you.
it.
I've explained this in
All
great
right.
detail.
Okay, we're coming up here to the end. I think what you're saying, Jerry, as I understand it, you're saying is that we can define We can sort of understand what Newton was talking about with his three laws of motion because we live on the Earth and we can test his three laws of motion relative to the Earth. Okay, so you can, if you have a guy on a piece of wood on a pond covered with ice, you can push that piece of wood out onto the pond covered in ice, and it will keep going and not stop. Okay, so yeah, so that proves Newton's for a law, right?
Well,
But the problem
it
is
applies all throughout the universe, but yeah.
the problem is you can define an inertial frame as a not as a sort of almost inertial frame on the Earth. That's what I understand your point being. We can
Well,
define sort of inertial frames on the Earth,
yeah,
but they're not what you call a stylized inertial frame. Is
yeah,
that correct?
yeah.
And so the problem is inertial frame is only an approximation.
Yes.
All
But
right.
because idealized inertial frames can exist, that doesn't prevent the validity of the concept and its usefulness, though. Even
Yes.
though,
Well, that's how mainstream would argue. Yes.
well, I don't know if they take it that far, but okay.
The problem also is the circularity of it. I mean, if you say, look, a body will continue in its state of motion or at rest unless and until it is experiencing an impressed external force, fine. But then, if you say, well, look, if and therefore there's an acceleration on those conditions. If you then say, well, this body is moving, and I don't know what's happening with the forces, but it actually is experiencing this acceleration. How do you know it's experiencing acceleration? Because I notice that there's a force on my body, either moving me back in my seats or moving me towards the windscreen, depending upon whether I'm accelerating or braking. It's really circular reasoning because in one case uh, you're defining acceleration in terms of this force, and in the other case you're actually defining the force in terms of acceleration. In other words, the departure from inertiality. So I think that's the central problem.
Well, I think the point is that once you've accepted Newton's laws, you've accepted the implicit assumptions behind his postulates. So he has Newton's laws are really postulates, and if you accept those postulates, then you kind of accept the conditions upon which the postulates are defined. Does that make sense to you? So we've accepted those postulates when we talk about inertial frames. So inertial frame means Newton's postulates apply. But the problem is that's just a mathematical idealization to allow you to do calculations.
It's observational. I mean, it isn't even necessarily subjective. I mean, you can observe that these effects occur, whether you're there. If you have set up like a car and you're observing just from the side in a stationary position, and you observe a car that's traveling at constant velocity, and you have it suddenly by radio controlled or however slam on the brakes, you will see like those crash test dummies. You see them slam to the wall like that.
Nobody's arguing this point, Jerry. That what
Okay,
you just said is
I
that
thought they were. I'm sorry.
the laws are confirmed by observations because the law by the scientific method that Newton presents. You know, he talks about he's presenting a science. His book is a template for the scientific method. So he makes these postulates, and then he says, "Oh, okay, we see these effects in reality happen. So therefore, my theory is valid because my mathematical model is confirmed by observations."
Yeah.
That's scientific method according to Newton. So nobody's disagreeing with that. The
Okay,
problem is that works only in the approximation of what an inertial frame is. The next problem is Einstein comes along and he says, well, I'm going to apply this inertial frame postulate to light. That's where the real problem starts to come in. And do you accept, and you seem to be saying you don't accept Einstein's postulate that you can apply this mechanical idea of Newton, his mechanical theory,
Well,
to light. Can we do this or not? That's what the argument really fundamentally is about.
well, when I mentioned earlier that I accept uh, Einstein's adaptation with the second postulate, I didn't mean anything of that sort. I meant simply that, you know, that there's possibly the presence of electromagnetism. That, okay, there's of course a second postulate that it's invariant. It's always the same velocity no matter what, however fast the observer or light source travel, which I personally don't know if that's the truth. However, though, yeah, I didn't mean to misclarify my views earlier about the presence of electromagnetism. I don't think that. I mean, if Einstein applied it with inertial frames, I mean, I'm sort of unsure what you meant exactly of that, but it didn't seem something that I agreed with.
Okay, so we're sort of in. Okay, I didn't really. We're coming up here on. We've got like 3 minutes, so I think we need to come to the end. I'm going to make I'm going to make an observation here that I didn't think that we would have enough discussion on your very brief little talk, but it turns out we have we have a lot of discussion. So I would like for you to, if you could, summarize what your view is, and sort of given all the questions, can you sort of summarize what you think you're trying to say?
Well, uh, I would say essentially that I agree with Galileo and Newton. Like Galileo expressed it in frames, Newton expressed it in objects. When there is an acceleration, when there's a constant velocity, and you don't turn, you don't slow down, that it creates an inertial frame or object, and that the Earth's stabilizing groundwork, as I've called it, that it counteracts all of the accelerations caused by the Earth's spin and rotation around the sun, to where there's a stabilized inertial environment with which to conduct effective experiments. Also, that within any two objects that travel relative to each other, okay, idealized inertial frames can't exist. However, though, if they experience the same degree of gravity, such as on Earth, they're effectively equally inertial, I would say. That basically sums it up, I would say.
All right. Yeah, well, that provoked a lot of discussion, I would say. Do you have any observations to make relative to cosmology as a result of this discussion that we've made?
Like in what sort of way? I'm unsure.
Well, we've talked about an absolute frame and the need
Oh,
for an
okay.
absolute frame and as a framework for cosmology.
Well, cosmology, like just as far as, well, it takes on different connotations as far as how the universe got here, like the true nature of the universe and such. So, I mean, I would say these inertial conditions set forth by Galileo and Newton, that they apply all throughout the universe. Sorry about the phone ringing there.
All right. Okay. Well, and do we have any final comments, or got less than a minute here? I want to thank you for taking the time to give us this talk, Jerry, and I want to thank everybody for
Thanks so much.
boy, what a spirited discussion. Wow, that kind of surprised me. Okay, and I
Thank
guess
you, Jim and Vladimir. I appreciate
and I want
your
to
comments.
encourage
Sir,
people.
many times I told you, sorry for my emotions. It's
Oh,
my
it's
mother
totally
nature.
okay. Sorry for mine.
Sorry,
All
sorry.
right,
Only I'm very happy with your emotions too. Believe me. But I am very solid physicist. I want
Oh,
to know all the notions you used. Constant velocity. What does it mean? Acceleration.